potential you would expect to get. Do you know what the cathode is? Do you know what the anode is? Well, then I probably would do that first, okay? I think we need to do half reactions probably first. We could probably do the net cell reaction second. If you want to do cell notation, third, fine. And then, of course, we can calculate the cell potential fourth. And we're also going to draw it as well, okay? And we'll draw it here as well. Now, I want you to think about this for a second. This one is tricky, okay? So we got a zinc hydrogen cell. Zinc hydrogen cell. Remember, if we want to make this, we have to have two parts. We need two half cells. So we have probably, my guess is, because I don't think zinc and hydrogen combine together in any equation that I know of from your data booklet, okay? I mean, maybe that's unfair for me to say, but I think most of you guys, we've done quite a few of those now. Have you ever seen zinc and hydrogen combined together on the same side? I don't think so, okay? So we probably have two half cells here, obviously. We have a zinc half cell and a hydrogen half cell. So I want to look for those things. What else has to be in those half cells for that reaction to take place? Okay, there has to be a transfer of electrons. We're telling you it's a voltaic cell here. This has to take place. We're talking about zinc half cell and a hydrogen half cell. What are the things that you can list out from those two? So go ahead and take a look. Find something. Some things you might want to write out here. Zinc. Right? Okay. I'm thinking that, once again, zinc is probably going to be one of the half cells. If zinc's one of the half cells, what goes with zinc? Zinc 2+. Right? The most common type of half cell is a metal dipped in its ion, right? Solution. Probably zinc 2+. Yes? Okay? Fine. All right. Now you have an option right now, guys. I mean, I just still don't know if this is the cathode or the anode, or I don't know if this is going to, if zinc 2+ is going to gain 2 electrons to give you zinc solid, or is zinc solid going to lose 2 electrons to give you zinc 2+? I don't know, okay? You still have to do the other part. Hydrogen. Well, hydrogen half cell. What's another option for the hydrogen half cell? What else do I need to write down here, possibly? Nope. H+. Okay? So find hydrogen, guys, on your chart there. Okay? This is taking place in a solution, right? Okay? So we need to look on your chart. You need to find these so that you understand what's going on here. We got 2 half cells. We got a zinc and a zinc 2+, which are going to go together. Okay? And we've got a hydrogen half cell, that's all it says, hydrogen, but I also probably have to have some acid that goes with that, okay? Because that's the 2 sides there. Basically what I'm doing is, in case you're wondering here, you're looking at the options for each of these cells, right? Hey, if I got a zinc, probably what goes with that is a zinc 2+, and yes, you look left side, right side, and probably write both of those down. Zinc, I can find zinc solid there, and on the other side is zinc 2+, yes? That's probably the most common thing that's going to happen between those two. The only place you're going to find hydrogen is a little ways up there. It's on the right-hand side, I believe. Yes? And on the left side, you're going to see H+. So that's got to be my other half of this. Okay? And those two would go together as well. And of course, you're going to have, yes, some water as well. Okay? But these are the two that you're basically looking at here. Okay? which one is the most likely out of those four things there? Out of those four, which one's the most likely to gain electrons? What is it? Most likely to gain electrons? H plus, right? So a zinc hydrogen half cell, most likely to gain electrons is going to be that H plus, gaining electrons to give you that hydrogen gas. Okay? What's the most likely thing to lose electrons there? Well, zinc, obviously, right? Bottom right, working up. Okay. Now, some people are going to want to say, well, what about, what about the H2? I see H2 up there. Why didn't we pick that? Because I actually have that, right? I mean, that's part of the original list. And the answer is, well, if you pick H2 as the SRA, working your way up, and you pick zinc 2 positive, because people say, oh, well, I know zinc 2 positive, right? My question to you is that a spontaneous reaction? That's the key, right? You have to make sure it's spontaneous, all right? So the OA has to be higher than the RA. So we have to make sure we understand that and that we keep that in our minds, okay? This is higher, top left, than this is, right? Spontaneous. So all together here, we're going to write out our redox reaction. Once again, otherwise known as the net cell reaction. Make sure you know all these terms, of course, okay? So what do we have? 2H plus and zinc solid gives me H2 gas and zinc 2 positive. Okay? And that would be your net cell reaction or the redox reaction. All right. Well, I guess we could probably do cell notation for this. So let's do that. Here's my anode right here. Okay? So what would I do? I'd start here. I'd say solid chunk of zinc is my anode. What's my anode electrolyte? Well, turns into zinc 2 positive. Right? What is my cathode electrolyte? In other words, what's gaining electrons here? What's in that solution? 2H plus. We don't need to write down the 2, of course. H plus is gaining electrons. Okay, in water, aqueous, yes. And finally, what is, H plus. But don't forget, we also need to put the H2 gas in there as well. Because H2 gas is not a solid, simply a gas, of course. So that is part of my electrolyte. That's going to take place in that solution. You're probably going to get some bubbles being formed, yes. Okay. And finally, what's my solid here? Carbon, or we don't need another line there. Carbon, okay, or graphite or platinum would be my cathode electrolyte, or cathode, sorry, electrode. Okay? So that would be cell notation. If you wanted to draw this out, it would look something like this here. Real quick here. Okay, here's your half cell here. This is your anode half cell. Cathode half cell. Okay, here we said zinc solid gives me zinc 2 plus aqueous. Okay, electrons travel up through there. This is carbon, and down here, of course, we have H plus aqueous changing into H2 gas is what you would see. Yep. It can be any of those. Salt bridge, of course. Anions go towards the anode. Cations go towards the cathode. Okay? And that's kind of what the diagram would look like for that one there, zinc hydrogen half cell. Okay? Good? Questions, anyone on that? Questions? The net cell potential of this, how many volts could I expect to get out of this? Let's see. We'll take the net equals the cathode minus the anode. So you'll take the cathode. The cathode is a hydrogen half cell. If you look up that on your data booklet there, the cathode half cell, okay, is 0.00 volts minus, if you look up the zinc half cell, it's a negative, what is it, negative what? 0.76, negative 0.76 volts, okay? We subtract those two, of course, 0 minus a negative 0.76 volts, and we will get a positive 0.76 volts. I'll give you a little hint here as well. Anytime you see electrical, cell potential as a positive, positives are always voltaic cells, always. Okay, and we'll talk about that a little bit later. That's part of the thing that's another thing we'll be doing here. So, anytime it's positive, it's a voltaic cell. If it's negative, it's something different. All right. So positive 0.6 volts, 76 volts. Cathode minus the anode. Let's do this one. Okay. Once again, iron 3 and tin 4 cells. Once again, if you're thinking about half cells here, iron 3 and tin 4 half cells. Well, what else could I possibly have in these half cells then? Okay. Iron 3 and what did I say? Tin 4. Yeah? Okay. Those are two, like I said, probably not, obviously those two aren't combined together. We need two half cells here. So iron 3 plus aqueous, what's going to go with that? What's the most likely thing to go with that? Well, once again, look in your data booklet. Find iron 3 plus, left side or right side potentially, because we don't know if it's the cathode or anode. We don't know if iron 3 plus is going to gain electrons. Maybe it might lose electrons. I don't know. Let's look in the data booklet and find out what's most likely to happen here. Iron 3 plus, what goes with iron 3 plus in your data booklet there? Iron 2 plus. Okay, so let's write that down. Okay, what about tin 4 positive? What's the most likely thing to go with tin 4 positive? Find it on the left side, find it on the right side. Tin 2 plus. Okay, well, looks like to me so far, I don't even have a solid electrode here, do I? I don't have any solids here. That's okay, not a big deal. Okay, but I've written down what tin 4 plus can turn into tin 2 plus, or tin 2 plus can turn into tin 4 plus, depending on which way I write that equation. And I know iron 3 plus turns into iron 2 plus, or iron 2 turns into iron 3, depending on which way I write that equation. So I start with my list now. Okay, obviously there's going to be water in here as well, by the way, guys. I would doubt that that's kind of part of this equation here, but we already kind of have that with the aqueous thing there. Water is obviously another part that we could have written down here. But if we look at those, well, 5 things or 4 things, really, I mean, that's ultimately what you're going to have. When you look at those 4, which one is the most likely to gain electrons? So you start top left, right? Which one is the SOA? Top left, and start working your way down. Is it iron 3 plus, 2 plus, 4 plus, or 2 plus tins? And it's probably iron 3 plus, right? It's the first one you come across, correct? So we write this as SOA, and we say, okay, iron 3 plus obviously would gain an electron to give me iron 2 plus aqueous. This is your reduction half reaction. This happens at the cathode. Okay. What's the most likely thing to lose electrons? Well, it shouldn't be too much of a surprise now. Obviously, tin 2 plus, yes. Tin 2 plus, you're going to work, by the way, you're going to work bottom right and start working your way up until you find one of those other 3 things there. Obviously, it's not going to be the iron 2 plus, okay? you're going to be looking for tin 4 plus or tin 2 plus. It's got to be the tin 2 plus, right? Because that needs to lose electrons to turn into tin 4 plus, right? Okay? So, quite often, if you understand electron stuff here, you're going to understand that it doesn't matter, right? As soon as you figure out the cathode and that one's gaining electrons, the other one has to lose electrons, so you're kind of limited on what you're going to pick there, right? All right? So, let's see. Reduction oxidation half reaction, or the net cell. Add these two up here. Now, these two don't balance, so times 2 here. So 2 Fe3 positives and Sn2 positives gives me 2 Fe2 positives and Sn4 positive. Okay? There you go. You could do net cell potential for this, of course. What could I expect from the combination of these two half cells? Well, once again, let's maybe do cell notation first. Let's do that first. Cell notation, I want to start with the anode. What's my anode in this case here? Oh, by the way, this is the, what does it say? That's your SRA there, right? What is the anode in this case? Well, look up there. There's no solids, right? No solid chunks of metals. So I need to probably say carbon solid here. Okay. What's the anode electrolyte? Well, it is right here, tin 2 plus, which turns into tin 4 plus. So I'd say tin 2 plus aqueous, tin 4 plus aqueous. That's all part of my anode electrolyte. That would be in the bottom part of that cell, right? The electrolyte part. What's the cathode electrolyte? Well, Fe3 plus, aqueous, and Fe2 positive aqueous. Fe3 plus is turning into Fe2 plus. So that's your Fe3 plus, Fe2 plus. And of course, once again, I don't have a solid for my cathode, so I have to use, again, carbon here. Which one did you put first or whatever? And no, as long as you know that's the anode electrolyte and cathode. But as far as the actual ions there, no, it doesn't matter. You'll just see a list of them. Usually you're right, kind of, you know, tin 2 plus turns into tin 4 plus, and iron 3 plus turns into iron 2 plus. You don't have to, though, okay? As long as you see that somewhere there, okay? So that would be your cell notation. Next, you would have to do electrical potential, right? So Enet equals the cathode minus the anode. We're going to do a little bit more with that tomorrow, of course. The cathode number, what's that? What? Yeah, 0.77 sounds right. And this one here, oh, sorry, minus the anode was 0.15? Okay, 1.5. So your net here, okay, is positive 6.2. Okay. Now, one thing I want to point out, which is your next slide here at the bottom, it says this. But just so you understand what that slide's saying is this. When you go to calculate the net cell potential for these, you'll notice up here, this is the cathode, this is the anode. The cathode, I had to multiply by 2 to balance out the electrons, correct? Right? Yes? When you do cell potential, net cell potential, you do not ever multiply those numbers on the right-hand side. You just, whatever that number is the number you use, okay? So somebody might be asking me, well, this is your cathode here, don't you have to multiply that by 2 to match it up with the electrons that was lost and gained? And the answer is no, you do not, okay? You simply just, see those numbers there? You just take them and use them, always. You never flip those numbers around either. So notice, this positive 0.15, okay, I just looked, positive 0.15, and I just wrote that down. You don't flip those. You never flip them. You never multiply them, nothing. You just take those numbers as they are. You leave them alone. Okay? Never ever, don't do anything to them. Okay? So you don't have to flip them, you don't have to change signs, nothing like that. And that's basically what they're saying here. The reduction potential for a half reaction remains constant, whether that half reaction is multiplied by a balancing coefficient or not. Whether you're using it as an oxidation half reaction or a reduction half reaction doesn't matter. You simply take that number and use it. Okay? That's all you need to worry about. Good? By the way, one of the things we didn't do here let's go back to the very first example here. It's been a while since we did this anyway, so we probably should talk about this. You know, if you want to talk about some observations here, which I want you to copy down here, guys. Observations. We haven't done this for a while, so probably a good thing to review. The thing is with these half cells, you're going to see two distinct things happening here. You're going to see what's happening here, okay, in the anode part, and you're going to see what's happening here in the cathode part. They're very distinct, of course, because you do have two half cells. So what's happening in the anode? What could you tell me about this? Well, let's see. Copper solid is getting used up, correct? It's turning into copper 2+. So I'd expect the mass of copper solid, of course, to decrease, right? Remember I showed you that picture of the electrode on Thursday? I showed you those two pictures. You got them in your notes, but they were up here. And then you remember how the zinc electrode was kind of eaten away at, right? Changed form from zinc to zinc 2+. Well, that's what you would see with this one. Copper would change from a copper solid. It would get used up, eaten away kind of thing, and would turn into a copper 2+ ion. The copper 2+ ion, by the way, because of that, you would expect a blue color to appear and to get darker and darker as this reaction occurs. So blue color to appear, because the copper 2+ ion is bluish, okay? And like I said, probably get darker over time. Other than that, as far as this side goes, that's probably all we could really say about that side. Like I said, it would get darker over time. On the other side here, observations at the anode. What would be happening there? Well, let's see. This is a solid chunk of carbon here, so that has nothing to do with it, really. We don't need to worry about that. Well, let's see here. This is an acid, of course, so the pH looks like to me would be going what? From an acid, because remember, these two things here, the dichromate and the acid, are getting used up. Those are gaining electrons, and they're turning into chromium 3+ and water. So I would say the pH is probably going to go up in this case, yes? From an acid to more neutral, correct? Okay? So pH would go up. Dichromate, there's a color with that. What is it, orange? Yeah? I would say the dichromate orange color disappears. Okay? Forms chromium 3+. Well, chromium 3+ is a blue-green color. So a blue-green color would appear. Okay? Blue-green color would appear. As far as masses of anything, that wouldn't be going up or down or anything like that. I guess the last thing I could probably say here, chromium 3+, what else? I would say the last thing, if you wanted to, conductivity here would probably go down as well, right? Because you're going from a positive and a negative, acid and dichromate, to 3+ and water, which of course are, you know, once again, less conductive, right? You need some negatives there to conduct electrical current. So you would say that probably in that part right there, the conductivity would be going down. Okay? Good? So before, we were kind of doing it as a, like I said, as an overall reaction. Now what we would say is we'd focus on each of these half cells and see what's actually going on in both of these parts here. All right? Good? Any questions? And you could do that with the other ones, of course, as well, but I think that one did say observations, which I kind of skipped over, so. Okay. Any other questions before we get going here? Questions, anyone? All right. So, you got some